Hey there, it's Max, and we are going to do the AES Counter Fun Challenge. Drew wrote this, and I think it's a pretty cool challenge. I think crypto challenges can be kind of scary, but after I understood this, I actually had a really good time with it. I think he did a really good job, and it was really fun. So let's read the prompt. I heard about this new AES mode called Counter. It allows us to encrypt messages of any size. How does it work though? For context, AES is a symmetric encryption algorithm, meaning that you're going to take some data, you're going to scramble it, and you're going to get it back. And then you can use the same exact key to descramble it and get back the original. Apparently, it generates a key stream that's the same size as our plain text, and then just XORs it with the plain text to get the ciphertext. How's that key stream generated? Well, it's related to the key and nonce somehow. Can you see if I did something wrong here? Hint, there are two ways to solve this. The first person to find both ways will get a special prize. Tell the coach if you find both ways. One of the ways is very elegant, the other way is brute force. Choose wisely. So, let's look through the program. The first part of the program, it's reading some random data, and it says key and nonce. We can see that it's passed into the cipher, which means this is likely the key and the nonce being used. The key is the data used to, the secret information used to encrypt the data, and then the nonce is an additional value which is used, but the nonce or usage depends on the AES block cipher mode. So I said that AES is a block cipher, but there are various modes of block ciphers. One of them is called counter, and I'll explain how it works in a moment after we go through this program. So encrypt will encrypt the information using the random key and nonce that were generated, and then it prints out the encrypted flag. So we have to somehow decrypt that. Finally, it has a while true, and it takes in your input, and then it will encrypt said input and print it for you. So if we go here, we can interact with that. So we can see that this is the flag and asks us what we want to encrypt. So we give it a bunch of A's, and you'll notice that this is a lot smaller of a key stream, and that's not key stream of a ciphertext. It's hex data though. And interesting property of this, if we add one more character, we'll actually see that the plain text also slightly increases in size, which is interesting. Sorry, the ciphertext increases in size. I find this really interesting because that means that counter mode acts more like a stream cipher as opposed to a block cipher. In most block ciphers, if you have extra characters, because it's done in groups or blocks, it will pad those out, but this mode does not do that, which is interesting. So this is how we interact with the program. Now we're going to talk some about AES counter mode. I tried doing this before, it didn't go very well, so we'll try it again. Most algorithms are with AES, you use AES encrypt with the key and that algorithm over the plain text. And then you do something with the nonce. Maybe you XOR it. There's other things you can do with it that I don't think are really that relevant to go into. But in AES counter mode, it's a little bit different. So the counter is literally meant to be like an incrementing value. The reason counter mode exists is because it has some pretty cool properties. For instance, with a lot of block cipher modes, you have to decrypt all of it if you want to get to a particular block, which is annoying. But with counter mode, if you know the nonce of the encrypted data, you can just get that particular value. And that's really nice. So there are real world use cases for counter mode, but if you do some things wrong, then it doesn't work very well. And there's a lot of issues you can have. So in AES counter mode, it AES encrypts the nonce and then XORs it with the plain text. So the key stream is generated from this. So if there's a way to leak this for a particular thing, then you actually know the key for that. And that's a problem. And if we look here, there doesn't seem anything that's like really obvious. For those who've been doing some crypto things in the past, nonce actually stands for number only used once, I believe. And you see here that we're actually reusing this nonce over and over again. And that turns out to be the issue. Reusing nonces in AES is a very bad thing to do. It completely breaks the entire algorithm if you do that. But why is that? Because of the properties of XOR. So in this case, this is the ciphertext. And with XOR, if you have two values, and if you know two of the values, you can always recover the third. And that's an important property of XOR for this attack in particular. So we're going to spell out the operations that are here based upon what we know already. So we're going to say the encrypted flag is equal to the AES encrypted nonce XORed with the flag. Additionally, if we have our information, we can do encrypted us equals AES of nonce XOR with our data. So we'll say us again. So at first glance, this doesn't seem like a big deal, but this is where it gets cool. We can do some math. If we XOR all of these together, then there's a problem. If you XOR two numbers together, for instance, if we do this in Python, if we do 2 XOR with 2, it's 0. And this is because XOR has the weird property. I guess that's just how XOR works. 0 and 0 is 0, 1 and 0 is 1, 0 and 1 is 1, and then 1 and 1 is 0. So if you XOR something with itself, it's always going to be just zeros. So what happens here is that the AES nonces, the encrypted AES nonces cancel each other out because they're the same information, because we're reusing nonces. So what this leaves us with is it leaves us with the encrypted flag XORed with, it leaves the plain text flag with our unencrypted information. And I think that's pretty interesting. So our goal is to take this and XOR all the information together until we get the proper key. So we're going to go, I was using that before. We're going to go to our program, and we're going to get the values. So this is our encrypted flag for this round. And then this is 38 characters. We can also do that math real fast. We can just do this, take the length of it, and we want it divided by 2 because it's the hex characters. So we're going to do flag, or encrypted flag equals this. And then we're going to encrypt our data. So we're going to do A times 38. And then it's going to give us back some new ciphertext. So that's what we have there. And we can add that. We can do inc plain text. Oop, I forgot to put the hex cursor on it. And then we also need the hex encoded version of all of the A's for the plain text at this point. So we're going to do 41 times 38, and that will give us what we want. So we're going to say plain text. So at this point, we're going to do all of those shenanigans that we were talking about. So we know the flag's in here, we know our plain text is in here, and we know these are in here, and we are given output. So these cancel each other out, like I said. And like I said before, if you know you need two, you can recover the third. We know the output. We know our plain text, so therefore you can recover the flag. All we have to do is XOR all of them together and we get the answer. So we're going to do encrypted wait, did I do something wrong here? Oh, okay. We're flag XORed with plain text XORed with our plain text. And if we take the hex value of that, you'll see that there's a lot of really nice characters here. If you've looked at ASCII or hex that should be ASCII enough, you'll notice that there's a bunch of pretty values. For instance, we have 5-3. We have 4-3. I know 4-3 is C. 3-6 is 3. Or sorry, it's 6. And so this should ring a bell. This is SCC, which means that we have found the flag. We just gotta take this to some website that will decode it for us. Cool. So now that we have done this, we're good. And there is our flag that we can submit. So again, the key to this challenge is understanding, I guess this is the elegant solution. I need to explain the brute force one still. The key to understanding this is how AES counter mode works and XOR. There's a reason this is really bad. You can't reuse nonce in AES counter mode. It's because you can use these XOR properties to get back the original plain text that you want to see. So the brute force solution is how I actually solved it initially. To me, it makes a little bit more sense. But that's also okay with the nonce. So when we're reusing this nonce, because we're using that, it means that the same effective key stream is going to be used over and over again, which is pretty nice. So we see the encrypted flag here. We can see that it's just 5B. So if I try like the character 1, you'll notice that it returns hex 39. If I try 2, it returns 3A because it's reusing the same key stream over and over again. So what's cool about this is we can try the same one over and over. We can try all these over and over again until we get the proper value. We're not brute forcing the entire string. We can brute force it character by character. And it's only 256 possibilities. But in reality, it's a ASCII string, which is much less. It's more like 70 characters or something. There's not that many things it could be because we know it's a string. So we can do that over and over again, but we happen to know that the first string is likely to be S. And if you look at that, it's 5B. If you do B, it's 4A. If you do C, it's 4B, which is also what I was expecting the right answer to be. What is the flag? Let's see. Did I look at the wrong one? All right, we'll try this again. We'll do, because we need S3. That's why. Okay, so what I messed up on is I was just typing in C, but I need to type in SC because the key stream is unique to the particular index in the key. Cool. So those are the two solutions for this. Thanks to Drew for writing this. I think it's really fun. I think it's a good introduction to modern cryptography once you start to get outside of things like Caesar ciphers. A lot of modern cryptography is understanding the various properties of things and having a good time with it. So, thanks for watching.